I hope you are able to see the whiteboard.
Yes, sir.
Yes, yeah. Okay. So that is what the interpretation from your end, right? So I said there is a difficulty in what analysis of the bandpass signal and as well as bandpass system from equations 1 and 2. What I said, it complicates the means the term, the exponential term or exponential factor, which is there in both the bandpass signal representation and as well as bandpass system representation, complicates the analysis of the bandpass system, which is driven by the bandpass signal. So to overcome that difficulty, I said there are two ways. One is the time domain procedure, another one is the frequency domain procedure. So in the previous class, we have discussed about the time domain procedure, and we have arrived at the equation that we can express the in-phase component and as well as the quadrature component of the bandpass signal of a bandpass system in terms of the in-phase and quadrature component of the impulse response of the bandpass system, which is convolved with the in-phase and quadrature component of the bandpass signal. Okay, so that is xi of t is equal to 1 by 2 into hi of t convolved with si of t minus hq of t convolved with sq of t. And another one is xq of t, that is quadrature component of the bandpass signal, which is equal to 1 by 2 hq of t convolved with si of t plus hi of t convolved with sq of t, right? So here this hi of t and si of t or sq of t are all low pass functions, I said. So with that we will be able to simplify the analysis of the bandpass system and as well as bandpass signal. So let us see how can be done this thing in the frequency domain. Okay. So frequency domain procedure. Okay. So in frequency domain procedure, let me start with the expression of rating. I think equation 8, what I have written, equation 8, any one of you can say, what is equation 8? If you have noted, I think we'll be able to say what is equation 8. Yes, I need your support. Yeah.
X side of t is equal to 1 by 2 integration minus infinity to infinity h side of tau, sir, actually.
Yeah, h side of tau into
S side of t minus tau.
Tau into d tau, right? So basically, it is the what out that is the it is what it is a complex envelope of the output signal of a bandpass system, right? Sir, no. So
Yes,
let me take the Fourier transform of that. Okay. So I hope all have written that equation, because I will not be able to go back. I will be asking you people to say what is that equation 8, 9 and all. So from equation 8 I will write. Okay. From equation 8, I hope that equation 8 what one of your friend is said is x side of t only, right? So if I take the Fourier transform of that, okay, if we take the Fourier transform of that, what do we get? Any one of you can say. If we take Fourier transform to that equation 8, yeah, so there it is written in terms of convolution integral, right? Integral. So what will be its Fourier transform? Yeah, Fourier transform. So it is x tide of t is equal to 1 by 2, right? Integral from minus infinity to infinity h tide of tau into s tide of t minus tau into d tau. See, if I take the Fourier transform, what I can write? X tide of f, right? Hope you all agree with me. I can write x tide of t, its Fourier transform will be x tide of f, which is equal to 1 by 2, okay, into h tide of f into s tide of f. Yes, is this fine? Yes, I'm asking, is this fine? By taking Fourier transform, I can write the equation 8 as like this. X tide of f is equal to 1 by 2 into s tide of f into s tide of f. Okay. Means basically what I am doing here, I am writing the Fourier transform of the impulse response of the complex bandpass system, and as well as the Fourier transform of the uh, complex low pass representation of the bandpass signal, right? So this is what the expression of x tide of f. So to begin the frequency domain procedure for a simplification of the analysis of the bandpass signal and as well as bandpass system, I start with this, right? So now looking at this expression, so what will be the first step? What I need to determine by looking at the above expression, I need to determine h tide of f. Yes, the first thing is I need to determine h tide of f. Then I know how to evaluate this one already, right? Then multiply those two, you will be able to get this x tide of f, and take the inverse Fourier transform, you will be able to say what is its equivalent in time domain. Okay, so that is what the procedure is. So the first step is we need to determine what is h tide of f. Okay. Determine h tide of f. So how do we do that? So hope you are aware of this h tide of f minus fc, okay, which will be equal to 2 into h of f, 2 into h of f for f greater than 0. Yes, are you aware of this equation? I said while discussing about the bandpass system, no, I told the time domain procedure, and I asked you people to do in the same way for time frequency domain procedure. If you have done that, then you will be able to say, okay, h tide of f will be equal to, means I can determine h tide of f with this expression, that is h tide of f minus fc is equal to 2 into h of f. Okay, if you have not done, then you have to look back. Okay, so first thing is that, then after finding or after determining the h tide of f, then I said we need to evaluate this complex envelope, that is h tide of f, right? So how do I do that? The second step is evaluate the complex envelope. So S tide of T. So I'm writing in time domain. So I know what is S tide of T. So I can express S tide of T is equal to what? Si of T, right, plus J into SQ of T. Is this fine?
Yes, sir.
Then I can find out what is the Fourier transform of this. No? Then I will get S tide of F. So okay, compute and then compute Fourier transform. Okay, so I hope you understand. If I write just Ft, that is S tide of F I get. So after doing that, what is the third step with respect to the equation 14? What I can say, I can compute X tide of F. Right? X tide of F will be equal to 1 by 2 S tide of F into S tide of F. After doing that, I can take the inverse Fourier transform of the above equation. Okay. So compute inverse Fourier transform. Compute inverse Fourier transform. Then inverse Fourier transform of X tide of F. Okay. To get X tide of T. Right. Okay.
Sir, can you scroll up a bit?
Scroll up. Okay. Yeah. Is that fine?
Yes, sir.
Yeah. So once I find what is X tide of T, then I can find out the desired output signal. So what is desired output signal? That is X of T. Compute the desired signal desired output signal, I can say. Compute the desired output signal, so which is what X of T, so which is equal to what real part of X tide of T into is a e power j2 pi fct. Okay. So to summarize, to sum up this, what I can say is the low pass equivalents of the incoming band pass signal and the band pass system will work by eliminating the exponential factor, that is e power j 2 pi of ct, from the computation without the loss of information. That is what I wanted to conclude with the this topic. Means so in frequency domain, just we take the Fourier transform and we multiply those two things, we will be able to calculate what is x side of f, right? By taking inverse Fourier transform, yes, we get x side of t. Then from that we say what is x of t. Right? In the time domain procedure, we know how we have done that. Okay, how do we express the in phase and potential component of the x of t, right? Yes, is it fine? Yes, I am asking, is it fine?
Yes, sir.
Okay, so let me take the next topic, that is line codes. Yeah, I think it is little bit already known topic what I am taking today, and we will be discussing some more extension to that what we have discussed in the previous semester. That is, we have discussed about various line codes, na? Right? Any one of you can say quickly what are the different types of line codes we have discussed? Yeah, I expect answer for this because already these things have been studied, isn't it? It is not new, totally new. Yeah, rest of some of the things I can say is what you discussed in first module. It is very basic. Okay, so if at all you want to be in core of this communication, I think module 1 plays a very important role in especially the understanding about the importance of representing bandpass signal and as well as bandpass system in terms of its complex low pass representations. Okay, I think I hope I convey to the extent of understanding and applying these concepts in further coming topics. Okay, yeah, so at least it is a known topic, no? Line codes already. This topic has been discussed in the previous semester, right? Quickly, I wanted to know your the understanding or what you have remembered so far. Yes, hope you are able to see my slides. Yes, are you able to see my slides?
sir.
I'm asking.
Yes, sir.
Yeah, yes. Can I expect any answer from any one of you? Line codes.
Sir, unipolar,
Unipolar NRZ,
bipolar.
Unipolar Z, Manchester, bipolar.
Okay, okay. So these are the different types of line codes, what you're saying. Good. Yeah, anybody else? Add to Skanda's answer? Nobody? Okay, fine. Yeah, able to see now? So basically, these line codes are classified into unipolar, polar, and bipolar. Okay, even one more level I have shown, that is multi-level. So just take it unipolar, polar, and bipolar, right? So before already we know what is unipolar, polar, and bipolar. I think people should be able to say that. So before that, let me just give the basics of that. Okay. Yeah. What I'm saying here, unipolar encoding, right, uses only one voltage level. Means 0 will be represented by 0 volts and 1 will be represented by plus 5 volts. Okay. That is why it is called unipolar. Hope you are understanding what I'm saying. Yes,
Yes.
my dear students. See, when I ask the previous hour's topic content, also you will not respond. How I can expect you to answer for the previous semester content, right? At least some students are responding good. So again, I'm going with the basics. So even basics only we are discussing in this semester also, not with mathematical this one, as I said in the previous semester also. So in the first one is what I said, unipolar, right? Unipolar. So here we use only one voltage level to represent the binary data, right? So here digital data is what? We have zeros and ones, right? So 0 will be represented by the 0 voltage level and 1 will be represented by the plus 5 volts level. That's all. So that is why it is called unipolar line code. Hope I am clear.
Yes, sir.
Okay, so before I take up the next one, just I wanted to say this. So what I said here, see 1 will be represented with plus 5 volts and 0 will be represented with 0 volts. So these are the two signal levels, right? And two data levels are what? So 0 and 1, right? 0 is one data and 1 is another data. So hope you are understanding this, what I am saying. 0 means 0 volts and 1 means plus 5 volts, I will say. There is a signal level, we say. Okay, data level means data is what? 0, 1, 0, 1, binary data, right? So that is the data. Even I can have 3 signal levels, okay? And still that data level is only 2. That is 0, 1, 0, 1 is the data, right? I can have a 3 signal level. That is what? I can represent 0 by 0 volts and 1 can be represented either plus 5 volts or minus 5 volts. Okay, the data 1 can be represented by plus 5 volts or minus 5 volts. And then data 0 will be represented by 0 volts. Then I can say that type of line coding will be having 3 signal levels. Hope you are able to understand what is a 2 signal level and what is a 3 signal levels and what is a data level. Yes, my dear students should respond.
Yes.
So data level means it is a digital data, okay, zeros and ones. Signal level means how I represent that data, digital data with what voltage level, right? I said 1 is 0 is represented by 0 volts and data 1 is represented by plus 5 volts. So in that case, I have 2 signal levels and 2 data levels, right? And another one I said, I can represent the digital data 0 by 0 volts and digital data 1 by either plus 5 volts or minus 5 volts. Okay, in that case, I say it has 3 signal levels. Okay, and data level is only 2. Okay, so having clarity about this, let me take up the next one. And this is also, it's all additional information, basics which you need to know. So if I say DC component, no, the first one is having a this signal is having a DC component, right? So you all know DC means at 0 volts, that is at no frequency, right? Frequency is 0 hertz. So here I represented data 1 by plus 5 volts and data 0 by 0 volts, right? So this particular data encoding technique is having a DC component, what I can say, right? The second one, okay, another signal here, this signal will not have any DC component because here I am using data 1, okay, data 1 is represented by plus 5 volts and data 0 is represented by minus 5 volts. Okay, so with that, this particular signal will not have any DC component. Fine. Yeah, another thing is lack of synchronization, we say, right? So what do you mean by that? Lack of synchronization. The first diagram shows the data sent 10110001 like that, right? So the second one, if the clock is very fast, right? So you will be able to means this is the data sent and this is the data received at the receiver side. Okay, if I have a very fast clock, what is happening? There will be no synchronization between the transmitted signal and the received signal. Okay, that we call as a lack of synchronization. Okay, so lack of synchronization is what? There will be no synchronization between the transmitted data and the received data. Okay, that is what we call as a lack of synchronization. So synchronization is must to get the proper recovery of the transmitted signal at the receiver side. So all those things, why I'm stressing on that is I need to have or I need to encode the digital data such that all these things means it should not have DC component, it should have synchronization, built-in synchronization, so that the recovery of the signal at the receiver side becomes easier. So that is why I'm just showing what is lack of synchronization, what is a signal with DC, what is a signal without DC. Hope these two things are clear. And what is a different signal level also I said, right? Yeah. So with this, let me take up the next one, that is polar encoding. Okay. So this polar encoding uses two voltage levels. Okay. That is data 1 is represented by plus 5 volts and data 0 is represented by minus 5 volts. Okay. Yeah. Yes, here I have shown the different types of line codes. Okay, of course, you are all, yeah, first one is what? Unipolar. NRZ means what? Anyone can say what is NRZ?
Non-return to zeros.
Yeah, non-return to zero, right? So here I have taken an example of a binary data is what? 11010001. Okay, 11010001. Okay. Is able to see the movement of the slides? Yes, my dear students. Are you able to see the movement of the slides?
Yes, sir.
Yeah. Okay, I think this slideshow is better.
Sir, can you put it to presentation mode? Because it's very...
Ah. Now in the slide, this is a slideshow. It is not visible.
No, sir.
So, like, can you make it full screen, sir? It's too
Yeah,
small.
that is what I. Yeah, that is what I made it full screen. That is a
No, sir,
slideshow.
it's not on slideshow mode, sir.
Just now I removed. You people said no, it is not working. Means, what about now? Yes, now is it slideshow?
No, sir.
No. Okay, let me go ahead with this. Yeah. So this line codes now I have taken an example of what 11010001 is my binary data. Okay, so you can leave the first one, that is punch type, just there. So here mark means I am representing with the dot, and space means no this one. Okay, let's start with unipolar NRZ, that is unipolar non-return to zero. I said unipolar means what? Data 1 is represented by plus 5 volts and data 0 is represented by 0 volts. And here NRZ, that is non-return to zero, means this pulse, no, I am representing data 1 by plus 5 volts, right? So it will be occupying the entire bit duration. So this TB I said right here, that is the bit duration. So it will be there high for entire bit duration. So next bit is also 1, that is why I continued with that. The next bit is 0, so it is of 0 volts. So next bit is 1, so it is 5 volts till of the entire duration. So this is how we say unipolar NRZ. Okay, means it will be, that particular pulse will be occupying the entire pulse duration. If it is high, it will be high for the entire bit duration. If it is low, it will be low for entire bit duration. That depends upon the data. So next, what I said, polar non-return to zero. Next one, right? So I said in case of polar, I represent data 1 by plus 5 volts and data 0 by minus 5 volts. So here I have taken that amplitude as plus A and minus A. So that value of A can be plus 5 volts and the value of minus A can be minus 5 volts. Okay. So it is NRZ again. So first 2 bits are 1 1. That is why it is represented with plus 5 volts. And the next data is 0. That is represented by minus 5 volts. So next data is 1. So I am representing with plus 5 volts. So next 2 data bits are 0 0. That is why I am representing with minus 5 volts. So next data bit is 1. So I am representing it by plus 5 volts. So for the entire bit duration, it will be plus 5 for data 1. And for data 0, it will be minus 5 volts for the entire bit duration. That is why it is called NRZ, non-return to zero. So next one is unipolar return to zero. So unipolar return to zero. We have already understood what is unipolar non-return to zero, right? So here unipolar return to zero means the data 1 will be represented by plus 5 volts, and here it will be high for only half of the bit duration. Okay, and it will come back to 0 for another half of the bit duration. That is why it is called return to 0. Okay, so return to 0 means what? In 1 bit, okay, that is for data 1, it will be high for half of the bit duration, and another half the bit duration it comes back to 0th level. Okay, because I am representing in case of unipolar data 1 by plus 5 volts, right? So it will be plus 5 volts only for half of the bit duration. Another half of the bit duration it comes back to 0 volts level. So next bit is also 1. That is why it will be plus 5 volts for half the bit duration. Again, for another half the bit duration, it comes back to 0. So next bit is 0. So it will be at the 0th level only. Okay. Only for 1, it will be coming back to the 0 for half the bit duration. Another half of the bit duration, it will be high. Is that fine? So next is 1, right? So half the bit duration will be high. Then it comes back 0. Next 2 bits are 0 0. So it is at 0th level only. The next bit is 1. So it is again high for half the bit duration. Another half the bit duration comes back to 0. This is why it is called return to 0. So next one is bipolar. Okay, even you can write. Yeah, even you can write polar return to 0. In the same way, can you just write and show me? Otherwise, I will be only keep telling from my side. Polar NRZ waveform is shown here. I expect you people to write polar return to 0 for the same sequence of data. And I will ask you people to present. Just take 1 minute time and do it. Polar return to 0. Yes, Rishabh Kumar. Rishabh Kumar. Shank. Rushank.
Yes, sir.
Can you present, man? Polar return to 0, I asked. What Rohit Joshi you joined just now? Rohit Joshi.
Yes, sir.
It is 10:70 now.
No, sir. I left in between network issues, sir. Again, I have joined, sir.
Okay, Rushank, can you just say? Can you project? Have written?
Yes, I'm doing it.
Yes, Mohan Sai. Mohan Sai. Yeah, can you present, man? That polar return to 0.
Doing 7 minutes.
Doing. ಎಷ್ಟೊತ್ತಾಗುತ್ತೋ ಮಾಡಲಿಕ್ಕೆ? It's very simple. What about Manish? Manish.
Sir,
Polar return to 0 waveform ತೋರಿಸ್ತೀಯಾ? ಏನು ಎಸ್ ಇಲ್ಲ ನೋನು ಇಲ್ಲಲ್ಲ, ಸುಮ್ಮನೆ ಆಗ್ಬಿಟ್ಟೆ.
no,
ಯು ಕಾಂಟ್. ಇದೇನ್ ಮಾಡ್ತಾ ಇದೀಯಾ? ಕೇಳಿಸ್ಕೊಂತ ಇಲ್ವಾ ಹೇಳ್ತಾ ಇರೋದು? ವಾಟ್ ಮನೀಶ್?
ಕೇಳಿಸ್ಕೊತೀನಿ ಸರ್.
ಮತ್ತೆ ಅರ್ಥ ಆಗ್ಲಿಲ್ವಾ? ಯೂನಿಪೋಲಾರ್ ರಿಟರ್ನ್ ಟು 0 ಹೇಳಿದೆ, Unipolar NRZ ಹೇಳಿದೆ, then polar NRZ I have told. Then I asked you people to do it polar return to 0. Return to 0, what I said, for data 1, it will be I for half the bit duration. Okay, and it will come back to 0th level. Okay, then for data 0, it will be negative value, right? It is minus 5 volts for half the bit duration. Again, it will come back to 0 for another half the bit duration. That's all. If you write that much, that will be your polar return to 0. Yes, Rushank, can you show? Rushank. Yes, what about Manoj? Manoj. Yes, Manoj. ಮಾತನಲ್ಲ ಅಂತಾನೆ. Yes, what about Girish? Girish.
Sir.
Yes, can you present, man, polar return to 0 waveform?
Yes, sir. Yes, sir.
Huh? Yes,
Hello.
Rushank, what happened?
Sir.
Rushank.
Hello.
ಯಾ ಏನೋ ಮನೋಜ್ ಈಗ ಅಲೋ ಅಂತಿದ್ಯಲ್ವನ ಮಾತಾಡಿಸ್ತಾ ಈಗ ಮಾತಾಡ್ತಾ ಇಲ್ವಲ್ಲ
ಸರ್ ಇಲ್ಲ ಸರ್ ನೆಟ್ವರ್ಕ್ ಸರ್ ಇಲ್ಲ ಸರ್.
ಏನ್ ನೆಟ್ವರ್ಕ್ ಯಾವಾಗ ಸರಿ ಇರುತ್ತೋ ಕೊರೋನಾ ಹೋಗೋವರೆಗೆ ನೆಟ್ವರ್ಕ್ ಸರಿ ಇರಲ್ಲ ಅನ್ಸುತ್ತೆ.
ಇಲ್ಲ ಸರ್.
ಎಸ್ ವಾಟ್ ಅಬೌಟ್ ಭಾರತಿ? ಭಾರತಿ
Yes, sir, I'm noting now.
not noting, man. You have to. Can you present? I am asking polar return to zero. Already I told orally. I am expecting you to present that. Yes, Ashwini C. Gujar.
Yes, sir.
ಯಾಕೆ ನೀವು ಮೀಟಿಂಗ್ ಬಿಡ್ತೀರಾ ಸೇರ್ತೀರಾ? ನೆಟ್ವರ್ಕ್ ಸರಿ ಇಲ್ವಾ? Just 2 minutes back you left the meeting and again you joined. What about Anant Kattani? Ananta. ಏನ್ ಮಾಡ್ತಾ ಇದೀಯನಾ? ಪೋಲಾರ್ ರಿಟರ್ನ್ ಟು ಝೀರೋ ಬರ್ದಿದೀಯಾ?
ಸರ್ ಎಸ್ ಸರ್ ಸರ್ ನೆಟ್ವರ್ಕ್ ಪ್ರಾಬ್ಲಮ್ ಸರ್.
ಆಯ್ತು. ಈಗ ಪೋಲಾರ್ ರಿಟರ್ನ್ ಟು ಝೀರೋ ಪ್ರೊಜೆಕ್ಟ್ ಮಾಡ್ತೀಯಾ? ಕ್ಯಾಮ್ರಾ ಆನ್ ಮಾಡಿ.
ಸರ್ ಡೂ ಅಂಡ್ ಶೋ ಸರ್.
ಇನ್ನೂ ಮಾಡಿಲ್ಲ. ಹೆಂಗ ಹಿಂಗ ಈ ತರ ರೆಸ್ಪಾನ್ಸ್ ಇದ್ರೆ
I'll do sir. I'll do.
What about Abhishek Reddy? Yes, Ashwini wanted to present.
Can you see, sir?
Yeah, I can see. I will just pin there. Okay. Okay, fine. Yes, Abhishek Reddy.
ಎಸ್ ಸರ್.
ಮಾಡಿದ್ದೇನಪ್ಪ ಪೋಲಾರ್ ರಿಟರ್ನ್ ಟು ಝೀರೋ?
ಮಾಡ್ತಾ ಇದೀನಿ ಸರ್.
ಇನ್ನು ಮಾಡಿ ಯಾವಾಗ ಮಾಡ್ತೀಯ? ಅಷ್ಟು ಟೈಮ್ ಆಗಿ ಹೋಗುತ್ತೆ ಅಷ್ಟೇ. It is just 1 minute job, man. Okay, I expect you people to show it in the next class at least. Fine. So then what is next one is bipolar return to zero. So bipolar return to zero. Bipolar means what? Here, in case of bipolar, zero will be represented by 0 volts only. The data 1 will be represented, that is by positive pulse once, and next it will be represented by negative pulse. Means if I have a consecutive ones, right, the first one will be represented by plus 5 volts and next one will be represented by minus 5 volts. Okay, hope understood this bipolar return to zero. In a given sequence of data, the first one will be represented by plus 5 volts and next one will be represented by minus 5 volts. Again, if I have next one, that will be represented by plus 5 volts and 0 will be represented by 0 volts only. Here what I have shown is bipolar return to zero. So as usual, so for first data 1, it will be high for half the bit duration. Again it comes back to 0 for another half the bit duration. Next again 1 is there, so it will be represented by minus 5 volts for half the bit duration. Again it comes back to 0 to the another half the bit duration. So next data is 0, so it is at the 0th level only. So next data is 1 and the previous is represented by negative pulse, so here it will be represented by positive pulse. Okay, so for half the bit duration, because it is a return to 0. Again it comes to 0. Next two consecutive bits are 0 0, so that is why it is at the 0th level. So next is 1, so that will be represented by negative pulse because the previous one was represented by positive pulse. Fine. So this is bipolar return to 0. In the same way you can write bipolar non-return to 0 also. Okay, so here I have taken few things and few are not shown, so those things you should be able to write and project to me in the next class. So bipolar NRZ I have not written here. I expect you people to show it next. The next one is Manchester. Okay, so here Manchester, as I said, data 1 will be represented by plus 5 volts for half of the bit duration. Okay, another half of the bit duration, it will be represented by minus 5 volts. Okay, similarly, the data 0 will be represented by minus 5 volts for half the bit duration, and another half the bit duration, it will be represented by plus 5 volts. Hope you got my point. I said in case of Manchester, data 1 will be represented by what? Plus 5 volts for half of the bit duration. Another half of the bit duration, it will be represented by minus 5 volts. So with this example, the first bit is 1. That is why I am representing with plus 5 volts for half the bit duration. Again, there will be a transition at the mid of the bit duration. So it comes back to minus 5 volts. Again, next bit is 1. Again, it goes back to plus 5 volts. It will be plus 5 volts for half the bit duration. Again, there is a transition from plus 5 volts to minus 5 volts at the middle of the bit duration. So next bit is 0. That is why it will be at minus 5 volts till the half of the bit duration. Again, there will be a transition at the middle of the bit duration to plus 5 volts. Okay. So there will be a transition in every bit duration at the half of the bit duration. That is from plus 5 volts to minus 5 volts, or from minus 5 volts to plus 5 volts, depending upon the data, whether it is 1 or 0. If it is 1, as I said, it will be plus 5 volts for half the bit duration, and it will be minus 5 volts for another half the bit duration. Okay, for data 0, it will be minus 5 volts for half the bit duration, and it will be plus 5 volts for another half of the bit duration. So this is, we call it as Manchester line coding. Okay. To say the differential Manchester encoding. So the transition will be taking it at the middle of the bit, and that transition is used for synchronization purpose. Okay. So the bit representation, I think it does not take this. Okay. So you just try to understand only one way how I represent data 1 and how I represent data 0 in Manchester. Okay. There will be always a transition from high to low or low to high at the middle of the bit interval. That is what is shown here. It's slightly in a different way. I think don't take this, otherwise you will be into confusion. Means confusion in the sense, what we are saying, this is the presence of transition at the beginning of bit time to say it is 0 or 1, right? So 0 starts with negative minus 5 volts. There will be a transition at the middle of the bit interval, then it will be high. Again, for 1, it will be plus 5 volts, then it will be a transition. So these are used for synchronization purpose, I said. Okay, so let us try to understand the advantages and the disadvantages of each type of these line codes. Okay, so we are discussing about unipolar, polar, bipolar, Manchester. In all the case, I can say non-return to 0 and as well as return to 0. So advantage of non-return to 0 is it is easy to implement, and I say modest bandwidth requirement. So we'll discuss this. How do we say it requires a modest bandwidth requirement? So based on the power spectral density. Okay, we'll see what are the power spectral density of each of the line codes. And cons is it has large DC component, NRZ, non-return to 0. It will have large DC component, so there will be poor transmitter receiver synchronization. Okay, because there will be no signal transitions for long strings of all zeros, right? So that is why we say there will be a poor transmitter receiver synchronization. So that is the drawback of this NRZ type of line codes. Okay. So advantage is what? It is easy to implement. It requires modest bandwidth. Disadvantage is it has a large DC component and there will be a poor synchronization between transmitter and receiver. Okay, it is used for magnetic recording. Okay, and not used much for signal transmission. So this is the application, what I can say. NRZ type of line codings. So don't worry about this NRZL and NRZI. Slightly, I think you don't have to take up this. Yeah. Then what are the advantages of return to zero? So return to zero type of line coding has lower DC content because the signal spends more time around zero. Okay. It guarantees an edge per bit. Means there will be always a transition from high to low, right? That is return to zero because, right? So that is why what we can say is it has better transmitter receiver synchronization. The disadvantage is it has higher frequency content because there will be a transition, right? It is only high for half the bit duration. So another half the bit duration comes back to zero. So frequency content, we say it is more. And as far as implementation wise, it is more difficult. So that is the drawback of return to zero. Yeah, I hope I conveyed. At least you should. I expect you people to do rest of the things. So let me continue further discussion about this line codes in the next class. So with this, I think I will stop.